Okay, hello everybody. In today's class, what we are going to see is we are going to review MOSFET operations. You might have learnt about MOSFETs in your first degree course, and also in this particular course, not the VLSI course, you have one course known as an PMMD, wherein physics and modeling of devices, in which you will learn a lot about MOSFETs, the physics behind it. Okay, what we are going to see is from a VLSI engineering point of view. We are just going to see how the MOSFET operates. Okay, we are not going to derive in-depth equations and get into the physics part of it. Okay, from the engineering point of view, we are going to see how an MOSFET operates. Okay, so that will help us in designing the circuits. Okay, so the aim is not to get into complex equations. The aim is to understand a little bit about MOSFETs so that we can design VLSI circuits with that knowledge. Okay, so the MOSFET is generally used as an switch in digital VLSI circuits, and since this course is primarily on digital VLSI, so we'll focus on MOSFET operation as an switch. Okay, initially, if you see here, how is an N MOSFET made? You have an P substrate into which you have an N source, which is an N drain, which is there in this, and then they are separated by a P channel, which is known as the length of the channel now here. So over the channel you have an insulator, which is TOX. That is the TOX is the thickness of the oxide. It is silicon dioxide. Was initially silicon dioxides were used. Now HFO2 is used, and over that you have a conduction layer, which is known as the gate. Okay, so gate was initially again made up of a polysilicon, and now we have aluminum, molybdenum, and things like that, other metals coming as a gate. Now here, let me just, since this diagram is already flashed, let me tell you. See, there is some N has got diffused below the gate. Okay, that is because how do we implant these layers? That we'll see in the next class in technology. But here, since this diagram is flashed, let me explain you. So we generally make the T oxide, and then we cut open here with the mask. We open these two areas. We just deposit silicon only on the gate area, and then we implant N and N regions. Okay, so some amount of N region gets diffused into below the gate also. Okay, so so you will have little bit of an overlap out here. Okay, I think is everybody having an issue with the screen? No. Okay. Okay. So this is in the cutoff region. Okay. So now when you don't apply any gate voltage, you will find this is N plus region, this is N plus region, and this is an P region. Now you will find when you are giving if you suppose you are grounding the source and giving a positive voltage in the drain, and you have given no voltage in the gate, so you will have between the P and N there is a diode. So this is a P region and this is an N region. So obviously a diode will be there, which will be reverse biased. Okay, so now the MOSFET is actually a symmetrical device. Okay, so when you make a MOSFET, you don't call this drain and source. It is the connections which you make that will make it a source or a drain. Suppose I give it a positive voltage out here, and I don't and I ground it here. So again this diode will get a reverse bias. So it is symmetrical device. So as long as there is no voltage available in the gate, and you given potential between the source and the drain, either way, either between positive here or here, one of these diodes will be reverse biased, and there will be no current which will flow. So this will act like an open switch. Okay, so now when you want this channel to conduct, okay, then you need to apply a voltage which is greater than the threshold voltage. Okay, it is not that you give a very slight gate voltage, it will start conducting. So there is something known as a threshold voltage. Okay, so whenever the gate voltage is above the threshold voltage, then this switch is closed, and now the current can flow between the drain and the source. Okay, so there is something known as a threshold voltage. That is the minimum voltage required for this device to switch on. Right now, what is threshold voltage? Okay, let's define what is the threshold voltage. So you see, when you apply a positive voltage out here, the first thing which happens out here is this P essentially has got a lot of holes, right? P substrate means the majority carrier he is going to be here holes. So those holes will start getting repelled from the channel area because of the positive potential which you have applied on the gate. So you will find there is a depletion layer region formed here. So the first thing on application of a voltage onto the gate will be a formation of an depletion layer. What is depletion layer? Where there is no free carriers, because in the P it is holes which is the majority carriers, and they are getting repelled because of the positive charge. And further, if you start increasing the voltage in the gate, okay, now the electrons which is available here, because of thermal agitation, so certain electrons will be there. Although it is P, there will be certain electrons which will be there, and also from the source and the drain region also there will be some electrons. So when you increase the voltage and further high, then certain electrons will come here, and now a channel is formed here. Now if you see, so this is known as inversion. Why this term inversion has come in is because this is P type, and now in the P region we are forming an electron channel, right? So it is an inversion. Instead of having an channel of positive holes, we are having an channel of negative electrons. Okay, electrons, right? So that is the reason we call it as an inversion layer. Okay, now the practical definition of VT is that particular voltage when the surface is said to be inverted, that is the density of the mobile electrons in the surface becomes equal to the density of the holes. Like for example, to start with, if my substrate has 10 to the power of 15 per centimeter cube density, holes per 10 to the power of 15 holes per centimeter cube, that is the hole density. Now VT is that voltage in which the density of the electrons in this channel will be 10 to the power of 15. Okay, if the substrate is 10 to the power of 16, then VT will correspond to 10 to the power of 16 electron density here. Okay, is this aspect clear to all of you? What is the threshold voltage? Okay, good. So now if you see the equation of the threshold voltage, it is a VTO. It has got 4 components. So let us just try and physically understand what are these 4 components. Yeah, it is per centimeter cube. Yeah, that's it. So that is the way we define the density of holes and electrons in semiconductors generally. Okay, not under channel. Yeah, the 10 to the power of 15, I said 10 to the power of 15 is the density, generally the density of the P substrate. And now when the channel is inverted, the density of electrons in this area where where channel inverted channel is formed, it should be 10 to the power of 15 electrons per centimeter square, centimeter cube. Okay. Here initially in the bulk region it is 10 to the power of 15 centimeter cube per centimeter cube. Now once the channel is inverted at the threshold voltage, when threshold voltage is applied at gate, the density of the electrons here will be 10 to the power of 10 to the power of 15 is not fixed. Okay, I am just giving a figure. Okay, just a figure. If it is 10 to the power of 16, accordingly that will be 10 to the power of 16. Okay. So now the threshold voltage component has 4 different unique components. Let's try and understand, without again getting into too much of physics and equations, what are these 4 components. Okay, the first one is known as work function between the gate and the channel. So this is gate, this is GC stands for gate, and the channel, this stands for the work function. Now you see a gate is generally made up of metal, and there are a lot of free electrons which are there, right? And the channel is a P substrate where there are holes. So when you get this gate close to this channel with a very thin layer of oxide or an insulator, so what will happen to these holes? They will start getting attracted towards the free electrons, right? So but our aim, what was our initial aim? To drive away these holes into the substrate so that an inversion channel is formed. So now you see, but this is what is just because we are getting this metal layer here, these holes are getting closed. So that is, we have now that additional work we need to do to drive away those holes back, right? So that additional work which is required, or additional voltage, is represented by GC, and the formula for that is this is the Fermi level work function of the substrate minus metal. Okay, if you are using a metal, and if you are using a polysilicon gate, then it will be substrate minus polysilicon. Okay, now is it okay? So so this is the way. So this is one component. Okay, why has this component come? Because we are using a metal and a P substrate, and these holes are likely to get attracted towards the surface because of the electrons available here. So we need to have a potential which to overcome that particular attraction, and that is given by phi GC. Okay, now if you see here, so different kinds of metals can result in different VT. Okay, so that is the reason, as of when the technology initially, we had a long channel device where you had a polysilicon gate, but now as we are scaling down the technology, we are going to like 45 nanometer, the VT has to be lesser than what is there in 180 nanometer technology, right? So we have aluminum for the N type. For the P type, we have molybdenum. So that there are a lot of metals which are used in a tungsten and all too. So the VT variation, like you have low VT devices, high VT devices and all. So this is known as gate engineering. Okay, gate engineering means the use of appropriate metal in the gate to adjust the VT of the devices. Okay, so this hope this particular aspect is clear to all of you about where does this phi GC came, work function. Okay, so the next is 2 phi f. Okay, yeah, it will be good if you keep writing messages in the so that I know I am online. Okay, so now the second is minus 2 phi f. Okay, so minus 2 phi f is the work required, okay, to invert this channel. Okay, from, so it is actually P type, and we have defined threshold voltage to make it N type. So the amount of work required, okay, voltage required to pull the electrons and push the holes. Okay, so that is given by 2 phi f. So this minus 2 phi f indicates the total voltage required to push the holes back and get equal number of electrons there. Okay, so if you said phi, now if you see the formula for that, it is kT by Q Ni by Na. Okay, so Ni is the number of free carriers available because of thermal agitation for at any given temperature, and Na is the doping concentration here, right? P, because this is a P type, so you have doped it, right? So this is, like we said, this is what I said, 10 to the power of 15 we generally take for long channel devices. For short channel devices we take it higher than that. So we have Na here, right? So now if you have Na is the concentration of the P type dopant here, right? Now if you see, this is in the denominator, so this is approximately Ni. For at room temperature it will be of the order of 10 to the power of 10 centimeter per centimeter cube, whereas this we have 10 to the power of 15. So this whole thing comes as negative. So again you have one more negative here, and you have another 2 out here. So 2 means first you have to push away the holes, and then you have to generate that much amount of electrons there. So this minus 2f is the voltage required for the channel to get invert. Now if you see here, Na, the higher the Na, so this will become this figure will become greater. So if you increase the doping concentrations here, okay, your VT will increase. Is that aspect clear to all of you? A difference between GC and what is the difference of purpose? Can you just work function? Can you just switch on your mic and speak, please? I'm not able to read the queries there.
Is it audible?
Yeah, it's audible.
So basically, there are two components, which is 5GC. This is the first one, and the 2.5 is the second one.
Yeah.
Now, from what I understood, is both are used to just like drive away the holes and to make the channel as P type as N type.
Yeah.
This
Correct.
is the so what is the difference of purpose of the work function here at the number one, and number two is like the 5F.
Okay.
And that there are some differences.
Yeah, no. See, there are primarily there are 4 different components which will oppose formation of channel. We need to overcome each 4 of them. There are 4 different causes. Okay, 4 different sources which will oppose the formation of channel. So we need to overcome them. Okay, the first one is you have a metal and you have an holes out here. So there will be a tendency for these to come over here. So there will be an inbuilt potential which will be built. So you have to apply a voltage to overcome them. Once you have overcome that particular inbuilt potential, okay, the next thing is to drive the holes below and pull the electrons. So these are, first you need to do this and then you need to do this. So both of them will be required for formation of the channel. Is it okay? Like suppose in a circuit, okay, it is like you have to ensure some current flowing in a circuit. There could be multiple sources which are opposing the currents, right? So your applied potential has to be they all get algebraically added up, and you have to overcome that. Okay, so GC is what is the full? This is work function gate channel. Okay, this is work function gate channel. Okay. So the first gate channel, there will be potential, inbuilt potential here, because you have P here and then metal here. So there will be an attractive force available here too. So that needs to be offset through GC. This is the work required, or the voltage required for pushing the holes below and getting the electrons here. Okay, so these are the things. So in-depth derivation of all these things will be done in your PMMD class. So now this is, although this is negative out here, the net effect will be positive, because in the equation, if you see here, this is 10 to the power of 10, this will be 10 to the power of 15. So this whole thing will come as a negative. So this will get added up. Okay, so this will be positive. The net effect, this will be positive. This will be also be positive. Okay, now there is another thing which is, yeah.
Sir, I have one doubt.
Yeah.
So work function will also be negative, right? Because Fermi level of substrate will be always lesser than the metal.
No,
So
it will be higher, I guess. It is the
yeah. So
work required for the electron to be pulled from the conduction into the free band, right? So metal, it is already, it will be very little bit of only energy is required to get this thing into free.
oh, okay, got
Right?
it, got it.
Okay. So now the third component is, okay, is CBOX minus QBOX by COX. So let's see. Okay, what is this component? Okay, now if you see here, okay, now once these electrons are here, so in between there will be a depletion layer. Depletion layer means there will not be any free charges here, right? Because the holes have been repelled out here and electrons have been pulled here. So in between there will be a depletion layer here. So it is like having an PN junction here with a depletion layer, right? So this is N, this is P. So if you P, and then it is like a diode out here with a depletion layer. So like even for diode you require some positive voltage, right? So inbuilt positive voltage is required, right, to to switch on a diode. Here the diode is in the reverse direction. Here you have N here, depletion here, P here. So you need to give that much again, that extra voltage again, so that this also adds up actually. Okay, this is negative because that electron density will be taken out here. So just understand, in this course, like, we are not going to derive each of them. We just have to understand what are these components, where it has been coming from, right? So this is the additional voltage required to cater for this diode which is formed in here, okay, between the N and P. Okay, so there is a depletion layer here, so we need to have little bit of extra voltage to overcome that potential also. So that is where this term has come in. Okay, now finally, when we fabricate these devices, so there will be some charges which gets trapped in the oxide layer. So this is purely fabric, this is not within our control. So when we fabricate these items, these devices, in the interface region, there will be some impurities which are trapped, or there will be some excuse me, my throat is a bit sore today. So if you see here, there will be some lattice imperfections. So that will cause some additional ions to be they get fixed in the oxide layer, so you need to offset that also. So these are the 4 different components of VTO. Okay, now if you see here, QBO is the depletion charge. Okay, this is the depletion charge. Now if you see here, we have to understand what are the parameters which affect these things. So this depends on the kind of gate which is used. Okay, and this is, now if you increase the density out here, then the VT increases. Okay, now so if you have to bring down VT, you have to reduce the density out here, right? If you reduce the density, doping density, if you reduce the doping density of P region, then when the gate voltage is not there, then this diode which is formed here, earlier we said, this diode will become weak and there will be leakage currents. So that is the trade-off, right? So if you increase the doping density, then during cutoff region there will be no leakage currents. There will be lesser leakage currents if you have higher P doped region here. And if you have a lower doping density, but higher doping density will reduce the leakage current, but that will increase the VT. Okay, so that is the compromise, or that is the trade-off which requires to be done. Okay, so these are the 4 different components of VT. Okay, so body, we are taking an example where body is grounded. So in the next case, we'll see that what if the body is not grounded. So there, like in many circuits, body will always be grounded, but here we have taken the body and source to be at the same potential. So but that need not be the case, especially like when we make an so for example, when we make an NAND gate, the transistor which is on top of one NMOS, the second NMOS which is on top, that source is not grounded here, so there could be a potential available there. So if I just simplify and say, that means if this is at a higher potential than the body, okay, I can call it the other way around. I can assume this to be my ground and this as a negative potential. Okay, so it acts like an one more a gate with a negative potential here, right? So if I like, there will be a possibility where the source is at a higher potential than the body. So I can view it this way. I can call this as ground and this as an negative potential. Okay, here, right? That means I can consider here, like, there is one more gate out here, back gate, on which there is a negative potential applied. Okay, so what will that do? So you have now 2 gates, one is giving positive and the other is giving negative. So the negative potential now will do exactly the opposite thing which the gate is trying to do, and hence the VTH will increase. So now you have to give that additional voltage, so that VTH increases. Okay, so you will have this formula VSB also, this voltage also. Initially VSB was 0, so they got cancelled. So this is known as the body effect parameter. Okay, so all this in depth you will learn in your PMMD class. So here we just have to understand how an NMOS is switched on and off. Okay, so these basic things we should know for this particular course. Okay. Now let's try and do a very simple derivation of the currents in MOSFETs. Okay, again without getting into too much of physics. Okay, just the basic derivations. Now if you see here, now this is linear region where a small VDS is applied. Okay, now gate voltage, we have applied a gate voltage which is above the threshold voltage. So a channel has been formed out here, right? And VDS is also small. As of now it is very small. So what would be the current equation in this particular case? Now channel has been formed. Now if you see here, we call VOV, that is the overdrive voltage, which is VGS minus VT. Okay, so we have applied some voltage VGS, out of which VT has been used up to create a channel. Okay, so that much of voltage is not available to us. Only the voltage which is above VT is available for us for further use of this device as a switch. So from VGS and we reduce VT and we call this as overdrive voltage, because this VT voltage has been consumed in creating a channel here. So that is not available here. Now the channel has been formed. Now what does this VOV over and above the VT does is, it gives me some charges in the channel which I can use for the conduction of current between the source and the drain. So if you see the capacitance formula, okay, if capacitance is what, Q by VOV, and if I define COX as the oxide capacitance, which is per unit area. Okay, so COX into W into L. So this is the L here, W is going in the other dimension. Okay, so you have W into L. So this is the total capacitance here in this channel region. Yes, and this is Q divided by OV. Okay, so so this is the formula wherein the overdrive voltage will induce charge which is available for conduction from source to drain. Okay, there are more electrons here. Okay, but that is just to maintain the channel. So this additional voltage VOV that will induce a charge Q depending on COX WL, which is available for me for current conduction between the drain and the source. Okay, now what is the charge per unit length? Okay, unit length will be Q divided by L. So here I bring down the Q here, so it becomes COX WVOV. Okay, now what is the electric field in the channel? Now the electric field in this channel is W is equal to width and L is the length of the channel. Okay. So electric field is the voltage between the source and drain is VDS. Electric field is voltage per unit length. So I divided by L. Now the velocity of the charge in the channel is given by mu n E. Okay, so this is the velocity of the any electron in the channel. Mu n is known as the mobility of the electrons. Okay, so you multiply it with the electric field, so you get the velocity. Now E can be replaced by VDS by L. So this is what the velocity of the electrons in the channel. Okay, now if you multiply the velocity with charge per unit length, okay, you get the current. Okay, so now you multiply V into Q by L. So this is like VDS mu n replace and Q by L, this we found out COX W VO. So if you do that, now this is the final current equation. We get ID is equal to mu n COX W L VGS minus and VDC. Okay, now you see in this equation you will find that if you have greater width, the current will be high. If L is more, then the current will be low, because what happens is if L is more, then the electric field decreases. Like electric field is VDS by L, so that's why the current decreases. If you increase the overdrive voltage, obviously if you increase VGS minus VT, then more number of charges will be there. So mu n is the mobility. Okay, it depends on the mobility, and COX. So this is the equation, which final equation which we need to remember. Okay, here that is for a small VDS out here. Right now, if I this small VDS, if I plot the VDS versus ID, so it will be it is linear. Like ID and VDS are connected linearly here. So this is this is only for small VDS. Okay, the situation changes when I make VDS slightly larger, and the slope will be given by VGS minus VT here. So you can use this as a variable resistance also, for small VDS. For some purpose, if you require, you can modulate this gate voltage and use it as a variable resistance. Okay, so this is the plot between ID and VDS, and mu and COX is generally in we call it as trans conductance parameter Kn dash, because once the device, this depends on the technology, which as a circuit designer I don't have a role. Okay, if you see in this equation, okay, mu and COX as a circuit only the device, one who designs the device, he has got a control of mu n and COX. Okay, mu n also varies, we'll see that later on. But from the circuit designer point of view, from a VLSI designer point of view, I don't have any control of these things. So they are known as the transconductance parameter Kn dash. Okay, this is fixed for the technology. For each technology, it will be different. So for 180 it will be different, and for 45 it will be different. So we just have these W, L and VOV in our hands to design circuits. Okay, so this is how the MOSFET behaves in for small VDS variations. Okay. Now we have after that, if we keep increasing VDS, what happens? Okay, now let's try and understand this graph here. So at the source side, you have a VGS being applied. Now out of this is a VD. Okay, and rest of the V over drive voltage, the entire overdrive voltage will be used to create a channel. So channel looks like this here, right? And while coming to the drain side, we have applied VDS, now slightly more than VDS. Initially we were talking about very less VDS, so this straight line VDS was almost on the x-axis, and hence the channel was straight here. Right, in this particular case we are applying slightly greater VDS. Okay, now what happens is, now if you see here, what about VGD? So this is VGD here. Now here, okay, this is VDS. Okay, this is the gate voltage, and VGS is the entire thing, whereas we have put VDS here. So now VGD is on this much. Okay, now if you see from this dotted line to here, okay, this is known as VGD minus VTH. Okay, this is VTH, right? This much minus VT. So this is the overdrive voltage from this dotted line, from the VT line, which is this is the VT line, from the VT line to this line, VDS line. So this is the overdrive voltage available at the drain side. So since it is excuse me, since the VGD is greater than here than VT here, we still have a channel here, but it is not as big as an source. So this channel actually gets tapered like this. Okay, now because you are giving a positive voltage here, so now between here and here there is no VT available, so this channel has got tapered out here like this. Okay, now the current equation gets slightly modified. So what is the current equation going to be? If you see here, VOV, now if you see here, this we initially took it as VOV. Okay, now we are going to take it as VOV minus VDS by 2. If you see here, here it is a total VOV, and here it is going to be VOV minus VD. Now you add these two and take average, so that we are assuming this is this to be a straight line out here and a perfect trapezium here, right? If you make that assumption, then it will be, here it is VOV, here it is VOV minus VDS. So you add VOV plus VOV minus VDS divided by 2. So this area, now we will get VOV minus VDS by 2. So this is the equation of the current here, okay, for VDS slightly increased. So I get the second current equation. Okay, so this is known as the, this is known as, this MOSFET is operating in the linear region. Okay, this is known as the MOSFET is operating here in the linear region. So this is the current equation. Now if you further increase the gate voltage, okay, then this line is going to reach here, where now VDS, okay, now VDS is almost equal to V, or it is equal to V overdrive. Now when VDS becomes V overdrive, now the potential between the gate and the drain will be overdrive, right? So it has come like this particular has come almost till the pinch off region, because now there is no overdrive voltage available if you keep increasing these two. Okay, now this, if you see here, this line has completely reached this junction where it is VD. If you further increase in VOV, then no, it will be less than VT here, right? So this channel gets pinched off here. So this is known as the pinch off region. Now, so this is known as the MOSFET has reached the saturation region. It cannot further increase any current here because the channel has got pinched off here. Okay, till that time, okay, you keep on increasing VDS, you will get higher current, but here the channel gets pinched off. Now no more, no further increase of current is possible because the channel has got. Now what is the condition here? It is VDS is VOV, right? So VOV, so that is the condition. So if I put VDS is equal to VOD, so this will become VOV minus VOV by 2, so VOV by 2, and this also will become VOV, and VOV I am writing VGS minus VT. Okay, so if I do that, so you will get this equation. Now this is the third equation which I get. Okay, this is known as the current equation of a MOSFET in the saturation region. Okay, so if you see here again, it is here in this region VGS minus VT square. Okay, so more overdrive voltage will give me more drain current. Okay, similarly a higher ID sat. Okay, similarly a higher width will give me higher ID, and lower channel length will give me higher ID. So we have to understand these and what are the factors which affect the drain current. Okay, so at least that much, even if you don't remember the exact equation, okay, when we design things, at least we should know how these factors affect the ID. At least that much should be known to us. Okay, so if I plot on a VDS and ID, so these are the kind of graphs which I get, right? So for this is, as you keep, this is the current is getting saturated. So for VGS less than VT, there will be no current. As you keep increasing VGS, okay, so the current will get saturated at a higher value. So because you are increasing VGS. Okay, so for one particular of VGS, it is going and getting saturated here. Now if I increase VGS, okay, it is going to get saturated at a higher value. So these where these lines are horizontal with respect to this, they are known as the saturation region, where the channel has got pinched off. And for a small VD, we initially saw that here it is linear, and when in this portion, this is linear, and then it becomes a quadratic here, because VDS and VDS is there, both is there, and then it gets totally independent of VDS. So there are the three different stages. In the first stage, if you see here, it is linear, then VDS quadratic, and then finally in the saturation region there is no VDS. So it is linear, then it becomes a quadratic, and then it becomes independent of the VDS. So this is what an ID VDS for MOSFET looks like. Okay. Yeah.
Sir, what is the limit to which we can increase VGS?
VGS is specified by the technology parameter. Like for an 180 nanometer technology, when I say it is in a 1.8 volt, then maximum VGS we can give is 1.8 volt. Okay, and VDS also 1.8 volt. Although it may withstand up to for reliability issues, because there will be some spikes which will come to the gate, right, when there are switching happening. So even on the drain side also, those voltages can go beyond the rated values. That's only for a small, but when I talk about constant voltages which we are giving static voltages, that will be specified by the technology, right? For 45 nanometer VDD is going to be 1 volt, and for 180 nanometer is 1.8 volt. So every technology will specify what is the maximum voltage. Okay, why the current equation doesn't have a variable for depth of the channel? Okay, you mean this depth? Okay, so actually we are having electrons flowing here, and the depth is generally is already taken care of by this depletion layer and the number of channel formation. So that is a vertical that particular depth is actually, you can say that as that depends on the channel width, right? So that is already taken care of, number of electrons per unit length when we have taken up. So that aspect has already been catered for. Okay. Now this is okay. Now when we see the MOSFET operation for an digital circuit, what is that? A gate can withstand 1 volt before breakdown, I guess. 40 Armstrong gate can handle around 4 volt. Okay, so each technology will define how much gate voltage it can withstand, right? So it depends on the dielectric which is all used here, like, right, and also upon the dielectric as well as the thickness of the gate oxide. So every technology will define what is the maximum which can be applied out here, so that this dielectric doesn't break. Okay, so if you give high voltage, then this dielectric will break, electrons will tunnel through this. Okay, then your device will break. So you can't afford to give voltage beyond the specified limits. Okay, so like MOSFET in a switch condition, we'll just see from the digital VLSI point of view. Okay, how this MOSFETs operate. So when we give 0 voltage in the gate, so there are 2 diodes which are reverse biased here, so no current should flow. But then ideally current should not ideally it should be 0, but practically we'll find that a few picoamperes current will flow. Okay, so that we saw in the first class also. Similarly, when and RF should be infinite ideally, but practically since some current is going in picoamperes, you can call RF will be in mega ohms or giga ohms. Okay.
Sir, I have one question.
Yeah.
So, according to this VI characteristics, right?
Uh-huh.
So, when you are having a high VGS, then your threshold voltage will also increase, right? VT will also increase, right?
No, when you are having an high
VGS.
Okay.
So, if you go back, then so VT is basically increasing, right?
VG.
If you increase, or it is basically independent. It is independent of that. I mean, when you increase the VGS, will there be any impact on the VT?
No.
Threshold voltage?
No. Threshold voltage is another VT is fixed.
Okay, okay. Because why I'm saying this, that generally when you move to the higher voltages, right?
Hmm.
From the library characterization point of view, let's say you are operating in one voltage and then you move it to the higher voltage.
Hmm.
What we are seeing is that your delay improves, right? That means your VGS, if you're moving from 0.65 volt to, let's say, 0.85 volt, your delay improves, but your leakage degrades.
Yeah, okay,
It
okay.
increases.
That is known as an VT variation with voltage. We will do that in the next few slides. Okay.
Okay, sure.
Yeah, yeah. Like you said, it will like whatever you observed. Now we have an explanation for that coming up soon. Okay. Yeah, as of now, we are talking about long channel devices where VT is fixed. After a small break, we will take on no, submicron devices where we will see how VT gets affected by these voltages. Okay, we'll see that. Okay, now I was talking about NMOS when we use as an switch. Ideally, it will be 0. Ideally, it has to be 0, but few picoamperes current will flow. Similarly, for an here ion practically it should get short circuited, but then IR on will be practically in few ohms. Basically, because when I talk about a mechanical switch or something, the moment you switch on, so whatever the source and drain will get shorted to each other, right? If it is an ID, but the current will be limited by the ID equation which we have seen, right? So it is the current in the channel is restricted by the ID. Okay, so that is why you have something known as an R on. High electric field at drain will pull electron. This is PMOS. Yeah, we'll see about the PMOS also. Right now, when we use, I have a slide on PMOS. I will explain that there. Okay, and now if you see here, when I use as a MOSFET as a switch, I can use a MOSFET, NMOSFET to transmit 0 and 1. So whenever I have to transmit a 0, it transmits it perfectly. Whereas when I have to transmit a 1, the output voltage maximum it can go is VDD minus VTN. So the reason is, now suppose I am applying VD here, right? Now the current is going to flow from VD to from the drain terminal to the source terminal. So that is how the positive flow of ions. So now if I talk about electrons are going to flow from the source to drain. So that is the reason I call this as source, because this is an N MOSFET and the majority carrier is electrons. And if majority carrier, so that is why where the majority electrons start from, that will be called as an source. Okay, so this is an N MOSFET. So listen carefully, this is an N MOSFET. Majority carriers are electrons, and the flow of electrons starts from the source to the drain. So that is why this is known as a source in this particular case. Now when I am trying to connect a VDD here and expecting this voltage to go to VDD, that doesn't happen, because the moment this voltage reaches VDD minus VTN, now the gate source voltage will become VTN. It cannot go further up, because now VTN is the at least minimum voltage required for this device to be switched on. So that is why the output voltage get restricted to a value of VDD minus VTN. That means an NMOS when we use as a switch, we can't use it to transmit VDD or a logic 1. Because the maximum output voltage available will be VDD minus VTN, so you don't get a full rail voltage. Okay, whereas if I have to transmit a 0 out here, okay, now suppose this node is already charged to VDD and I give a gate voltage here. now what happens is, now the electrons are going to flow from here to here and the positive charge is going to flow from here. So now this becomes the source terminal. So once this is the source terminal, if you see here, this is 0, this is VDD, and irrespective of the voltage out here, this device will be switched on and it will be able to pull the entire charge which is available on this load capacitance to 0 voltage. So it is a perfect transmitter of 0. Okay, so this is what an NMOS switch acts like. So it is it transmits perfect 0 but not an 1 properly. Okay, so if that is understood, then we take on PMOS. Okay, so in PMOS, what you have, can you explain once again? Okay, so this is an NMOS, right? So if you are trying to transmit the VDD out here, now this is VDD. And now this here we are talking about the load. So load is generally a capacitance, right, for all the MOS circuits. So this is the capacitance. So now the current, the positive ions have to move from VDD here. This capacitance needs to be charged fully, right? So but the moment this reaches VDD minus VTN, okay, this is the gate, this is the source, so this will get switched off the moment it reaches VDD minus VTN. Okay, so suppose this is 1.8 volt and VTN is 0.6 volt. The moment it reaches 1.2 volt, gate is 1.8 volt. You have given to switch on this gate 1.8 volt, so 1.2 volt. So now gate source voltage is 0.6 volt. Okay, if it starts further increase, then the gate source voltage will fall below VTN. So that is not permitted, right? It doesn't conduct further. So this voltage out here gets restricted to VDD minus VTN. Okay, but whereas if I have it 0 here, right, and then in this case, now the positive ions are going from here to here, or electrons are going to come from here to here, right? So that is why we call this as source, and here this is 0 here and this is VDD here. So this it can, irrespective of the voltage here, and this will be switched on. So it is switched on continuously. So all this charge which is available gets grounded. So this voltage can go up to 0 out here. Okay. Yes, the lowest potential will be 0. See, we are not changing the drain. This is only our the device remains same. It is symmetrical device. It is the same device. Okay, the moment I am connecting here drain and a capacitance here. Okay, so we are calling this as a drain and this as a source. Similarly, this is calling source as a drain. Okay, the MOSFET is symmetrical, perfectly symmetrical. You although in your schematic, okay, it might be written drain and source there, but they can work either ways. It doesn't make any difference, right? Only for schematic purpose, so that it is written drain and source. When you pick up even in the cadence or any software, drain and source will be written there, but they are symmetric, they are interchangeable. You don't have to make these changes here. Okay, the way the current flows in these devices, they define whether it is a source or a drain. Okay, not the alphabets which is written there. They are merely some alphabets written there for easy understanding. Okay, but they don't make them source or drain. What makes them source and drain is the way you connect it. Okay, so now coming about the PMOSFET. So it is here generally in the digital circuits. You have this is the P substrate, and whenever in the same substrate we have to make N and P devices. So for P devices we make an N well. So now this becomes an substrate for the P devices. Okay, N well, and then you have two P plus regions here and here. Now if you see here, a VDD will be given here to this body, like there in the body we grounded it. Here we are going to give it an 5 the VDD, because essentially because this body and this should not be forward biased, so we are giving a 5 DD. Now if you give 5 volt here, right, this will be switched off condition because this is 5 volt. Now this is an N well, so the aim is to drive away the electrons here and pull the holes from P region. Okay, so exactly the opposite. So in this case, to switch on this device, I need to give Vg is equal to 0. Right? If I give Vg is equal to 0, now if you find here, this body is tied to 5 volt. Okay, so now you will find holes are being pulled here, and since I am giving Vg is equal to 0, the electrons will be pushed below and the holes will be pulled into the channel region. So exactly the opposite that happened in NMOS happens out here. So here you have, for Vg is equal to 0, this device gets switched on, right, because you are giving positive voltage to the drain. So these electrons, now this 0 volt is going to this is 5 volt, this body is 5 volt, and the source is also 5 volt. Now if you see here, since we are talking about holes, we call this terminal as source, because positive charges are going to flow from the source to the drain. So this we give, right? So again they are symmetrical. Okay, you can connect it either way, but the source and drain comes from the way we do the connections. So this is for the PMOS, it is exact. Now I off here also has to be practically 0, and here, yeah, and also this is N well. What is the significance of the N plus region? Okay, this is the N well, right? So this has to be lightly doped, because if you dope it high, okay, then there will be, and like the Vt will increase, that we saw in the Vt equation. So this has to be carefully, the amount of doping has an effect on Vt. Now why do we make an N plus contact, N plus and then a contact, so that if you try to make between N and then you put a metal there, so there will be too much of an inbuilt potential there, then a diode kind of thing will be formed there. Okay, so to make this contact proper, we make an N plus out here, and then we make a contact, so that there is a smooth connection between these two regions. Okay, so this is very, when you highly dope it, it becomes very close to that, this Fermi level becomes close to that of an metal. And then there is an this actually, when we make an N plus, although a sharp boundary is shown here, but when we actually dope it, it will gradually from there will be a transition from N to N plus to this metal, so that there is no additional potential barriers formed here. Okay, so that is, so even in here also, if I go back to the N device also, wherever the body connection, did I show somewhere? P substrate, or okay, whenever this here also, whenever we take the body connection, generally we have an P plus region. Okay, I think there are slides coming ahead which will explain that. Okay, now if you see the again P MOSFET operation, it is very similar characteristics you will get. Only thing is, here it is drain source voltage, so so it is in the negative. Now if I call it as an source drain voltage, then this all will be positive here. Like, so if you see here, when VGS is VGS is 0 here, then you have G and S is 0. That means if you give a 5 volt here and a 5 volt here, then VGS will be 0. Right? So you have to just the way you interpret it. So if you give VGS is equal to 0, then it is VSG is equal to 5 volt. Okay, so that is the difference here. Right? When I give VG is equal to 0, then VSG will be 5. Okay, so that is this VSG is equal to 5, the top graph. Right? Similarly, when I give VG is equal to 5, then VSG will be 0. So that is the VSG bottommost lines. Okay, so that is the way, only the way we interpret, we write these things here. I can write all these things positive if I change this nomenclature to source drain instead of drain source. Okay, so that is the PMOS. Now when we use the PMOS as a switch, okay, now if you see, if I am applying VDD here, suppose I have to transmit a VDD here, So now VDD, this is the capacitance, and to switch on this PMOS, I have to give it a 0 voltage to the gate. Initially for the NMOS, we were giving VDD to the gate, and now in this particular case, we are giving 0 to the gate for this to be switched on. Now if you see here, you have given VDD here, and this is the source now. Now this becomes the source. Okay. Now the same transistor you have given VDD here, so this voltage keeps increasing. Irrespective of the voltage here, this transistor will remain switched on because source is VDD and gate is 0. So VSG in this case will always be VDD. So this voltage can come up to VDD, no issues at all. So now you see the PMOS is a good transmitter of 1. Whereas the same, now I'm not swapping this VDD. I am just giving a voltage here and I'm putting a ground here. So now this will start acting like a source. This becomes a drain because now I have charged it to VDD. Now I want to pull it to 0 here. I'm putting a 0 here. Now if you see here, this is the source, the voltage will start following like this, right? But when this voltage reaches VTP, right, then this voltage, this gate gets switched off because this is the gate source voltage, right? So it gets switched off. So now you will find this PMOS is not a good transmitter of 0. It is a good transmitter of 1. So this is the difference between an NMOS and a PMOS, that an NMOS can transmit a 0 properly and a PMOS can transmit a 1 properly. Okay. So this is how and MOSFET when an NMOS and a PMOS together in a chip which are placed close to it looks like. So you have a P substrate, you have a P plus here, and then you have the body connection. You have N plus source, N plus drain, and then you have an N well here, and then you have an P and then N plus here, which is the body connection out here, right? Okay, now if you see here in this particular NMOS, the body is P type and the drain is N, so this becomes a diode. So you have to ensure that the body is at the lowest potential available in the circuit. Okay, if it is not at the lowest potential, then this diode can get forward biased. Okay, so there will be so many N plus regions which is there in the screen is blank. Is it so? Okay. So if you see here, this body needs to be connected to the lowest potential available in the circuit. So if you see here, there could be in a big circuit, there will be an substrate here. There will be many N plus regions corresponding to various NMOSs used in the circuit. So all those wherever there is an N plus, there will be a diode formed like this. You have to ensure that there is no current flowing from the body to any of the N plus. So we have to put a connection to the body which is the lowest possible potential available in the circuit. Generally for a digital circuit, it is the ground, right? Similarly for an PMOS, this is N well and this is the P plus region. So we have to ensure that there is no current flowing between the P N junction formed like this, we have to ensure that the body is biased with the highest possible potential. Generally for a digital circuit, it is the VDD. Okay, so these are the biasings, body biasings. Okay. Now if you see here, in this particular case, one more example we take, you have an NMOS here, you have an NMOS here. Many students do mistakes in simulation also. We tend to connect this source with the body here on top of this here also. So the problem with that is, you see here, this one, there are two NMOSs which are placed here, right? Now this body you connect it with the source, the bottom one, and you put it to ground. It's okay, fine. So this entire substrate becomes ground here. But for this top device is here. Now now if you see here, if you tie the body and the source here. Now suppose if you are tying body and source here, body and source here also, and you have put a ground here, so the potential has become ground here. Now what happens is, Suppose this transistor is on for an input A is high and B is low. This transistor becomes on, right? This is an NAND gate. So since B is 0, this will be also be on. So you will have VDD coming here. Output will be VDD, and also at the source terminal of this NMOS also there will be VDD. But if you have tied these two like this, then the VDD will get shorted to ground. So you should not do that. So independently each body should be grounded. Is this clear to all of you? Yeah, okay. Anybody? Yeah. So when we design a circuit, okay, please ensure that all the bodies are taken separately and grounded. So you understand what is the logic behind that. Same holds good for PMOS also. Don't keep shorting the body and the source terminals. Each of these body terminals should be brought separately and put to VDD here. Okay, because there could be a possibility that this voltage is VDD is ground here. Okay, this could be ground here, right? There is a possibility, because if this is switched on, this is switched off, then this node can come to 0. So right, and this is also switched on, so this also can come to 0. So there is a possibility that this source voltage is 0. So if you do this shorting, there is a possibility that there is a direct path available between VDD and ground. So for an NMOS, all the body connections independently should be grounded, and for all the PMOS in the circuit, they should be independently connected to VDD. Okay, having body effect. Yeah, so obviously this transistor might have an body effect. Okay, so we can't, so there will be some VT increase. Okay, because they are not in the same potential, there will be some VT increase. Okay, so in case there is some critical circuit in which you can't afford to have a higher VT, there will be some situations like that. In that case, you can have like this, and you have a P substrate, and then you have an isolated N well, and then you make one more P well. Now this P substrate can be 0 out here. This P well, this is not a global P well, this is for this P well. So here you can connect the source and the body. So such things can be done. Now also these kind of double wells are used when we need to give separate voltage to the body voltage to modulate VTH. So like schematic trigger designs and all, there are certain applications in which we can give separate voltage to the body to modulate the VTH. Okay, so in that case we can use this double well. So this is not the global P substrate here, it is a P well specific for one set of devices or one device. So that also can be done. So yeah, obviously it involves a greater number of fabrication steps in that case. Yeah, so that can be done. So that depends on specific application. So these kind of things are also done. So this is to give we can give separate voltage to these body also. Okay, that we can do that. Okay, yeah, we will take a break. I think we have reached almost the end of this session. So this is the last portion. Okay, latch. Okay, now if you see here, this is an NMOS and this is an PMOS. Placed close to each other. So you have N here, right? So now if you find this is a P, this is an N, and this is an P. So this becomes an NPN transistor. Okay. Similarly, this is N base. Okay, this is P and this P. Okay, so this becomes an PNP transistor. So if you see here, if you make an equivalent circuit, this is the bulk resistance which is there in the bulk. This is the bulk N resistance which is available in the N. So this becomes an back-to-back connected transistors. Now if you see a current which is flowing like this, if it increases, a small increase in current will increase the bias voltage of this NPN, so more current will flow. More current will allow more drop across Rn, that will increase the current in the PNP. So this is like a feedback, that increase will again increase NPN. So this becomes a latch and it will continuously keep increasing the currents out here, right? So this is an undesirable thing. They will they act like a positive feedback network out here, right? So we have to eliminate this. So there are what we generally do is along the when all the end devices are placed, surrounding that we put an P plus guard ring, right? Similarly, when all the PMOS devices are put around that, we put an N plus guard ring. Okay, so these guard rings generally they prevent the latch. Okay, so that is okay. Let me explain this issue of latch once again. So now if you see here, this is an P substrate. You have two N wells, N regions here corresponding to one N MOSFETs, and close by you have an N well here. This N well, within the N well you have two P plus region, right, and, which is for the source and drain of the P MOSFET, and also you have an N plus region out here, so that you are giving the substrate this region, you are biasing it with VDD. Now if you see here, at this region which is in close proximity to this N and P region, here in the bulk P region you will find this is P, right, and this is N. This region is N. Now you have an N here connected here, and you have another N, this N. So this becomes NPN. So this becomes an NPN transistor, right? And since you have connected this ground here, so within the bulk region, because it is lightly doped, you can think of having an RP here. So there will be some stray resistance here. So this is RP. Similarly, this is within the bulk N region. So you have RN out here. So that is the resistance as we move across in this region. So you will have because this is N, not N plus, this is lightly doped, right? So there is an RN. So you find two transistors which are back to back connected here, right? So if you see this, now if you see here, if some current starts flowing here like this, that current will bias this voltage, this NPN, okay, because this current is there, a voltage across RP will bias this voltage out here, okay, bias this NPN into the forward region. So the current will start flowing. The more current when it starts flowing, there will be this voltage will come to will come towards zero, because there will be more IR drop here. So this will again increase the current here. So this increase in current will result in increase in current in NPN, and NPN increase in current will increase the current in P. So they are like connected in a positive feedback loop. So there are a few things which we need to do to avoid such latch. Okay, first thing is we can remove this RP and RN. Okay, that is what we keep putting tabs at regular intervals, right? So that is the reason we just remove this RN and RP, so that it is always this potential is always at VDD. Okay, so then if this potential is always at an ground, if we ensure that RP is not there, then this will always be ground. So that is why at regular intervals we put the tab connection. Tab connection is we keep putting this P plus region and keep connecting it to ground. So you have there not for each, it is not necessary for each NMOS you have one body connection. A few NMOSs together, you at a regular interval on the substrate you put this P plus region and you keep grounding them. Okay, that is one thing. Similarly for an for an P MOSFETs also, for a few devices clubbed together at regular interval, we put this. Another important thing which we need to know, how is an NPN formed? Okay, N is highly doped. This N has to be highly doped, the emitter and the collector, and the base has to be lightly doped. Only then a BJT will be formed, right? So for a BJT, it is P has to be lightly doped. Similarly, for an PNP transistor, N requires to be lightly doped in, right? So only then this no, transistor will act like a transistor. Okay, for that these have to be highly doped and P is to be lightly doped. So what we can do is, wherever there is a boundary, if you put in a P plus a ring, then it will prevent this BJT from formation. So there are two techniques, right? So one is by having this body connections at regular intervals, or putting an P plus. P plus will make this BJT very, very weak. Okay, so if you understand how an BJT works, you will realize that the current being coming from the electrons which is coming from the emitter side, if it has to be swept towards the collector, the P has to be lightly doped. So if you put a P plus ring, this BJT will become weak, so there won't be any BJT, so this latch formation can be avoided. So that is the reason we are putting this in a P plus guard ring across all the NMOS devices. Similarly, N plus guard ring across all the PMOS devices. Okay, so that is another way of doing it, is by putting an SiO2 isolation well between the P and the N substrate, right? So this is known as the shallow trench isolation. So this is known as the shallow trench, this is known as the deep trench. Okay, deep trench means it is going deep down, this is the shallow trench. So these are the few techniques which we can use to avoid latch. Okay.